Hey everyone, Mr. Fransky here. This tends to be a relatively challenging concept, so I wanted to go through these 6 homework assignment problems, just kind of to make sure that you guys have kind of a step-by-step way of doing these problems. So let's jump in. All right, so first of all, they're just looking for the area. So just taking one cross section out of here, so in this case a circle. All they want to know is what the formula is for the area of this guy in terms of x, right? So here it looks like x goes from -1 to +1, right? So it's running from -1 to +1, and each x value creates a different sized circle. Right at 0, you're going to have the biggest possible circle, and then at 1 and -1, you actually have no circle at all. It's going to go all the way down to 0. So this would actually create a perfect sphere if you were to make this. So let's see what's going on here. All they want to know is the area of one of these disks here in the cross section. So the solid lies between planes perpendicular to the x-axis at -1 and 1. The cross-section perpendicular to the x-axis between these planes run from semicircle -√1 over 1 minus x squared. So that's this bottom semicircle right here. That's -√1 minus x squared. To the top semicircle, +√1 minus x squared. So the diameter all the way across runs that entire length from the bottom semicircle to the top one, no matter where you are. Okay, so we have a cross-section that are circular disks with diameters in the xy plane. So our diameter all the way across, the distance from this bottom function to the top function, which is √1 minus x squared. So that entire diameter there, if I were to draw a picture of this circle, so if we have on the axis here, we have the circle. So if the diameter is like right here, the way I think about that, if I change colors here, so I think about a top diameter, or a top radius, right? That would be the radius right here. That would correspond to this guy right here. And then you could also think about having like this bottom value right here. So the purple value is the value of this function. The top right here, the √1 minus x squared. The bottom, the green, that's this -√1 minus x squared. And the entire distance, the blue, is going to be those two things added together. Well, that's just the same thing twice, right? It's the purple value 2 times. So that entire distance, you could think about it as a top minus bottom, kind of like we did in the area video. So if you think about top minus bottom, it would be √1 minus x squared minus the bottom function, which is -√1 minus x squared, which is √1 minus x squared, plus the same thing again, √1 minus x squared. So really the way I think about it is the distance to the bottom is √1 minus x squared, the distance to the top is √1 minus x squared. So that is 2 √1 minus x squared. Okay, so that's the diameter. That's the diameter. We just want the radius. If we want to know the area of one of these disks, we just need the radius. So if we divide that by 2, so the radius would be this whole thing divided by 2, divided by 2. So we divide it by 2, those 2's just cancel. So the radius is just 1 minus x squared, √1 minus x squared. So in the area of a circle, remember the area is pi r squared. That's some formula that would be very good to know for this unit. So if it's pi r squared, the area of this at any x value, so no matter what x value you're at, is going to be pi times this radius, square root 1 minus x squared, which is pi times 1 minus x squared, because the square is going to take the square root away. All right, so that's all they want. They don't want us to integrate it. If you did want the volume, you would just integrate this from what, -1 to 1, right, of that guy dx. Okay, but they don't ask us to do that, so I'm not going to. All right, next up, they ask for, so same base region, but the cross-section is squares. So this time we have squares at every spot. Now the base length of the square is still going to be the same as the diameter was for the circle up here, right? So if I draw that square, always go to data, draw a picture of this thing. The base length right here, so over here we had that radius was √1 minus x squared. The base length now is that entire length. So the base length here is going to be √1 minus x squared. So that's the base length of the square. The area of a square is just base times height, or base squared, right? So it's going to be 2 √1 minus x squared, whole thing squared. Make sure you square both of these, right? The algebra is what gets you killed on these problems. It's usually not the calculus. So that's going to be 4 times 1 minus x squared. Okay, or you could distribute the 4 minus 4x squared. Either one of these would be okay, right? I'd probably leave it like that. 4 times 1 minus x squared. Okay, so again, these problems, all they're asking for is the area of one of those cross sections. They don't want you to find the actual entire volume. But again, if you want to define it on this, you just integrate from -1 to 1, because every single one of those x's is going to generate a different square, and you want to add up an infinite number of them. That's kind of the goal. Cool. All right, let's take a look at the next one. So here, now we have squares with a diagonal. The diagonal value, too far, the diagonal is actually going to be lying in the circle. Okay, so the cross sections are squares with diagonals in the xy plane. The length of a square's diagonal is root 2 times the length of its sides. That makes sense because if this is like 1 down here and 1, this is 45, 45, 90, right? Triangles, this would be root 2. So in general, x, x, and root 2x, that's how long the diagonal is going to be. So that's going to be helpful in finding the base length of the square. So these squares, if you take one of them, so that distance across the middle, we've seen that a lot, right? So that's going to be this entire distance. That's our 2 square root of 1 minus x squared. We've seen that value a whole bunch of times, right? That was the entire diameter of the circle. It was the entire base length of the square. This time that is the diagonal. Okay, so if that's the diagonal length, just like we said before, the diagonal is root 2 times the length of one of its sides. Okay, so the diagonal is root 2 times the length of one of its sides. Let's call that x. So if I want to find x, I have to take the diagonal and divide it by root 2. So the side length here is going to be 2 root 1 minus x squared divided by the square root of 2. So in the area at any x value is just going to be that side length squared. So it's going to be 2 root 1 minus x squared over root 2 whole thing squared. So the top we're going to have 4 times 1 minus x squared. And on the bottom we just have 2. 4 over 2 is 2. So that is 2 times 1 minus x squared. So this one is actually bigger or smaller than the last one. Looks like it's a little bit smaller, actually. So if the base length is the distance from the bottom to the top of the circle, you get bigger squares. That makes sense to me because this diagonal is going to be longer here. If you lay that down, if you lay it down, it's going to have to get shorter. Those squares are going to get smaller. So if the square is smaller at each spot, the overall volume is going to be smaller too. Not looking for the volume here. You would integrate it from -1 to 1, though, if you were. Now we got equilateral triangles. You remember the formula for equilateral triangles? It's one of the ones we said in class was an important one to know. If it has side length s, then the area is equal to root 3 over 4s squared. You can prove that by using trig, by finding the height, right? This is s over 2, this is s. You can use Pythagorean theorem to find the height. It's a bit of a pain, but if we remember this formula, then we don't have to remember how to find it. So if the area is root 3 over 4s squared, s here is that number again, right? We have that 2 square root of 1 minus x squared. So the area at any point x, from -1 to 1, is going to be root 3 over 4 times 2 square root of 1 minus x squared squared. So that's going to be root 3 over 4 times 4 times 1 minus x squared. The 4's cancel. So we have root 3 times 1 minus x squared. That's all there is to it. Again, if you wanted to find the actual volume of this thing, which would look kind of cool, the peak, you'd have like a peak of the triangle coming up and coming down like a semicircle, and the sides would be kind of curved along here. It'd be kind of cool. So if you wanted to find the volume of that, you would integrate this from -1 to 1. So root 3 times 1 minus x squared. Just double checking my solutions to make sure that's right. Yep, that's what I got. Okay, moving right along. So now, once again, we're just looking for the area, but we have a new curve this time. Now we have this kind of parabola-looking thing, x equals y squared. So here we have planes perpendicular to the x-axis from 0 to 4. Okay, cross sections run perpendicular to the x-axis. We see these circles here that are perpendicular to the x-axis, so we're going to be integrating in terms of x. And it runs from negative root x to positive root x. So they have x equals y squared because that would be plus or minus root x. So if we think about this, we have negative root x down here. We have positive root x up here. So it looks like the radius of one of these circles, is just going to be root x. Because it's just 1/2 of the entire thing. 2 root x from bottom to top. So the area at any x value is just going to be pi times root x squared, which is just pi x. Not too bad at all. Okay, so that would be the area at any one of these spots, just be pi x. Checking my solutions again. Yep, pi x. Sounds good to me. Alright, next one. This time we have squares. So that square length along the bottom is going to be the entire thing from negative root x to positive root x. So you could do root x minus negative root x, right? Top minus bottom would give you the entire length of that blue line. But, I mean, we know the top is root x, the bottom is root x, so it's just 2 root x. So the area, any x value, is going to be 2 root x quantity squared. Make sure you get that 2 squared. So that's going to be 4x. That's all there is to it. All right, now they don't give us the picture, so we have to draw it ourselves. Same problem, though, so we still have this kind of parabola-looking thing that's laying down. So parabola looks something like this. Okay, this time they say the cross-section is squares with diagonals in the xy plane. So we have our squares coming up like this and going down like that. Okay, so the diagonals are going to be that 2 root x length. So you have a square. Diagonal has a length of 2 root x. Now remember, we did this in the last problem too, right? To get the side length, it's going to be this diagonal divided by root 2. So we have 2 root x over root 2. So the area in the x value is going to be 2 root x over root 2 squared, which is 4x over 2, which is 2x. There we go. If you wanted the volume, you would integrate that from 0 to 4, right? Because they said they want us to stop at 4. Now they said they're equilateral triangles. So you can kind of see that they're getting some repetition in here, right? They're trying to get you to do the same thing over and over again. So we have equilateral triangles this time coming out. Okay, so getting bigger and bigger as you go to the right. So if we have equilateral triangles, base length is going to be 2 root x. Area is root 3 over 4 times the side length squared, 2 root x squared. So that's root 3 over 4 times 4x. 4's cancel, it's just root 3x. There we go. Okay. Now we get into actually finding some volumes, I believe. Thank goodness. Yeah, so let's find the volume of the solid analytically. Analytically means without a calculator, so they just want you to do the algebra to find it. So first one we have here, solid lies between the planes perpendicular to the x-axis at x equals 0 and x equals 4. Cross-sections are perpendicular to the x-axis from 0 to 4 are squares whose diagonals run from negative root x to positive root x. So we actually just did this one with the area. Now they just want us to actually find the volume. Okay, so we have squares with diagonals, I believe they say. So squares are going to come out like this and also go underneath like that. There's our diagonal that runs from negative root x to positive root x. So we have these squares. Good idea to draw a representative subinterval here. So that length is going to be 2 root x. So side length is 2 root x over root 2. So the area at one spot is going to be just 2 root x over root 2 squared, which is 4x over 2, which is 2x. So now we have to integrate 2x. So we integrate, remember, a of x, in this case from 0 to 4, because that's how far they want us to go, dx. So that's going to be the integral from 0 to 4 of 2x dx. Let's pull out the 2. Okay, so we have 2 times x squared over 2 from 0 to 4. You can cancel those 2's if you want to, because you can pull the 1/2 out of the whole thing. Let's do that, why not? So we have just x squared from 0 to 4, so that's going to be 4 squared minus 0 squared, which is 16. There's a nice volume that comes out of this weird looking function, right? But it's not too bad. Okay. All right, so we got that one. Let's try the next one. All right, so here we have some funky looking circles. And they're running between these two functions, right? So we have y equals x squared is this guy right here, and we have 2 minus x squared is this upside down looking guy here. So let's think about one of those circles. The diameter of that circle is going to be the difference of these functions, right? Because if we subtract one function from the other, that's going to give us the length in between there. So the diameter here, the diameter of the circle, is going to be equal to the top function, which is 2 minus x squared, minus the bottom function, which is x squared. Right. So that's the length of our diameter. So then the radius is going to be that divided by 2. So let's see, this is 2 minus 2x squared over 2, which is just 1 minus x squared, right? Because we can break this apart, right? It's a heart or butterfly, as some of you call it. So 2 over 2 is 1, 2x squared over 2 is x squared. So that's our radius. So then the area of this thing at any x value, we're going to have to find those intersection points. They tell us where it is? Yep, it's -1 to 1. Probably a good idea to make sure that's where they intersect. At -1, this is 1, this is also 1, yeah, and at 1 they're the same as well. Okay, so the area of this guy is pi r squared. So pi times 1 minus x squared quantity squared. So then the volume is going to be the integral from -1 to 1 of this area, because every single one of those x values will have a different area. We're going to add all those together. So I'm going to pull the pi out front. And 1 minus x squared squared, I'm going to expand that out. So that's 1 minus 2x squared plus x to the 4th dx. So now we do some algebra. Pi times, so this is x minus 2x cubed over 3 plus x to the 5th over 5. And that's from -1 to 1. So that's pi times, so we have to plug in 1, plug in -1, and subtract them. So if we plug in 1, we have 1 minus 2/3 plus 1/5 minus, I plug in -1. -1 cubed is still -1, so it'll be plus 2/3. And plugging -1 here is still -1 when you plug it in here, so we'll have minus 1/5. Okay, so pi times, let's see here, so we have 1 plus 1, right, because this negative was going to distribute in all the way here, so we have 2 minus 2/3 minus 2 more thirds is minus 4/3, and then plus 1/5 plus 1 more 1/5, because we have two negatives there, so plus 2/5. So we have to find a common denominator here. Of course, you could stop even here, right? You can't leave the evaluators out here, but you could just you could stop here. So we have pi times, let's see. So we have to go to 15ths, I think. So we have 30 15ths minus, multiply that by 5 is 20 15ths plus 6 15ths. So that's all over 15. So that's pi times 30 minus 20 is 10 plus 6 is 16 15ths. Let's see here. Something looks wrong there. 30 minus 20, 10 plus 6 is indeed 16 15ths. Did I mess something up? Oh, no, that's right. I was looking at the wrong solution in the solutions manual. That is definitely correct. 16 pi over 15, or pi times 16 15ths is just fine. Okay, all right, marching right along. So number 5. Solid lies between the planes perpendicular to the x-axis at -1 and 1. Cross sections perpendicular to the x-axis at these planes. Squares whose bases run from the semicircle -root 1 minus x squared to root 1 minus x squared. So this is a circle with radius 1. Here's our top semicircle. Here's our bottom semicircle. Beautiful circle right there, right? Okay, we have squares, and the bases run all the way across. We have squares coming out like this. Okay. Alright, so squares all the way through. So you have to think about what the base is going to be there. So this is -root 1 minus x squared. This is root 1 minus x squared. So the whole base length there is going to be 2 root 1 minus x squared. So it's 2 root 1 minus x squared along the bottom there. So the area of one of these spots is going to be pi times that whole mess squared. So 2 root 1 minus x squared squared. That's pi times 4 times 1 minus x squared. And so if we read that pretty, it's 4 pi times 1 minus x squared. That's the area of one of them. So to find out the entire volume, we got to integrate from -1 to 1. I'm going to pull the 4 pi out front. And we have, let's see, this is 1 minus 2x squared plus x to the 4th. Nope, no, we're not squared. What am I doing? Just 4 pi integral -1 to 1 of 1 minus x squared. Just like that, dx. Much easier. Last one we had that thing squared, right? We had to do a whole lot of integration with that. This shouldn't be too bad. So 4 pi times x minus x cubed over 3 from -1 to 1. So that's 4 pi times, let's see, 1 minus 1/3 minus -1 plus 1/3. Now, some of you may have noticed by now, it seems like this one is always the opposite of this one because we have this symmetry here. You could find the area, the volume of half of it, right, and then double it. You could definitely do that. So you go from 0 to 1 and then double the whole thing. Just don't forget to double it. Alright, so this is 4 pi times 1 plus 1 is 2. Negative 1/3 minus 1 more third is minus 2/3. 2 is 6/3. 6 minus 2 is 4/3. So we have 4 pi times 4/3, which is 16 pi over 3, which is a solution that I was looking at when I was doing the last one, so that's why I thought 16/15 was wrong, but this is right. So 16 pi over 3. One more. So we got these semicircles again. So a top semicircle looking like that. Bottom semicircle looking like that. Okay. And this time it is, what are they? Squares with diagonals that run from here to here. Okay, so we have kind of diamond looking things that are going below and above the plane. The diagonal is lying in the plane here. This is probably the one I'm worst at drawing. Okay, so they go underneath the circle and above. So the circle, or the square, has a diagonal here that's 2 root 1 minus x squared. So then the side length is 2 root 1 minus x squared divided by root 2. Okay, because the diagonal is root 2 times the side length. So the area of one of these bad boys is going to be 2 root 1 minus x squared over root 2 quantity squared, which is 4 times 1 minus x squared divided by 2, which is 2 times 1 minus x squared. So that's the area of one of these squares. And we want to go from negative 1 to 1, so we integrate negative 1 to 1, 2 pulled out, 1 minus x squared dx. And we actually just did this integral, but for practice, why not do it again? Especially if you're only watching this problem. So we have x minus x cubed over 3, negative 1 to 1. That is 2 times 1 minus a third minus negative 1 plus a third. So let's see, 1 plus 1 is 2, so 2 times 2, minus 1/3 minus 1 more third is minus 2/3. 2 is 6/3, minus 2/3 is 4/3 times 2, that's like 8/3. Whew. And that's all there is to it. Alright, hopefully this was helpful for doing these homework problems. I love you guys, that's why I'm here. Have a great day.